The genetic algorithm is one of the most fundamental pillars of artificial intelligence. And in this video, we're going to add the genetic algorithm to a simplified version of the Flappy Bird game without using any libraries. By coding everything from scratch, you will learn how an artificially intelligent neural network actually works. The code is available on my GitHub, and you'll find a link to it down in the description right above the like button. So let's get started and have a look at how we're going to build this. To begin, we're going to build an empty screen in Pygame within which we're going to build all of this. In the next step, we're simply going to add the ground to the game, and we're going to follow that up by adding the pipes to the game. After setting up this environment, we're going to add the player to the game. Then we're going to add the player movement and make him act randomly. So the movement you see here isn't the result of any neural network, it is simply the random function telling it to jump or not to jump randomly. After we have added one player who acts randomly, we're going to create an entire population of players that all act randomly. In the next step, we're going to remove the random motion and replace it with a motion which is determined by a neural network. After that, we're going to create the natural selection process, which is going to determine which birds from the previous generation get to create the offspring for the next generation. And in the very final step, we're going to talk about some optional optimizations that we can add to make the algorithm run more efficiently. The timestamp to each of these sections is going to be down in the description, so feel free to jump around. So let's start things off by creating the empty window within which we're going to be building all of this. So to begin, we want to click on New Project, and then in the location box, I'm going to give the project the name NEFT Flappy Bird. NEFT simply stands for Neuroevolution of Fixed Topologies, and later on in the video, I'll tell you what that means. I'm going to leave the New Environment checkbox checked, and I'm going to press Create to create the project. Once the new project has been created, I'm going to go down to the terminal and write pip install Pygame because we're going to need Pygame to build all of this. And make sure that you check that it actually says that Pygame has successfully installed like it does over here. Let's start off by creating all the project files that we will need. There's going to be a total of 9 files and they're all going to be empty at the beginning. To create the first one, all you have to do is right-click on the project directory and then click on New and then Python file. After that, go ahead and enter the name of the first file, which in our case is going to be config, and press on enter. Now go ahead and repeat this process for all the file names that you can see on the screen right now. Most of these files will become relevant later on in the video, but let's create them right off the bat so we don't have to worry about that later on. And once you've done that, you should see a list of 9 files. To begin, only the config and the main file will be relevant. Let's start off and look at the config file. In this file, we're going to import Pygame, then we're going to set the window height to 720, the window width to 550, and finally, we're going to create the window, which is equal to pygame.display.setMode, and within the brackets, we want to add the window width and the window height that we just created above. That's all we need to do in the config file. Let's move to the main.py file we created a moment ago, because that is where we're going to have the main loop of the program. What that means is that it's going to contain a while loop, which is going to be responsible for refreshing the screen every frame. Starting with the imports, we're going to import Pygame, then from system, we're going to import exit, and we're also going to import config, which is the file we created just a moment ago. Once that's done, we're going to initialize Pygame and create the Pygame clock. I'm also going to include a function which allows us to quit the game window whenever we press on the red X symbol in the top right hand corner. So I'm going to define the function quitGame, and below that, I'm going to add a for loop for event in Pygame event get. And below that, I'm going to add the if statement. If the event type is equal to Pygame quit, we want to subsequently quit Pygame and exit. Moving on, we're going to define the function main. This function is going to be the home to our main loop. So we're going to create a while loop here, and it is going to run the entire time, so we're going to write while true. Within this while loop, the first thing we're going to have is a call to the quitGame function, which is going to be checking if the user is trying to close the window. We also want to make sure that we refresh the window every frame, so we're going to fill the window with the color black after every while loop iteration. Finally, we're going to set the frame rate to 60, and we're going to update the display by writing pygame.display.flip. And we're going to make sure that we call the main function at the very end of this file. If we run the project at this stage, you'll see that we have an empty window which we can now use to build the rest of the project. And since we added that quit game function, when I press on the red X icon at the top of the window closes. The next thing that we're going to create is the ground. And we will add the ground to the components.py file that we created earlier on. This file is going to be responsible for game components such as the ground and the pipes. In here, I'm going to import Pygame, and then I'm going to create a new class called ground. Within this class, I'm going to create a new class variable called ground level, and it is going to be set equal to 500. This variable simply determines how low within the window the ground level is going to be. After that, we're going to create a constructor, and within this constructor, we're going to pass in as an argument the window width. We're going to set self.x and self.y equal to 0 and ground.ground level respectively. And we're going to set self.rect equal to pygame.rect, and within the brackets we're going to pass in the coordinates of where we want the ground to be displayed, the window width, and the line width. We also need a way to draw the line within the window that we've created. So we're going to create the function draw, and it takes two arguments. First, of course, is the instance itself. And in addition to that, we also need to pass in the window within which we want to draw the ground. And to draw the rectangle, we can simply execute pygame.drawRect, and then as an argument, we first pass in where we want to draw the rectangle, which is in the window, then the color of the rectangle, and finally the rectangle which we want to draw, and that is self.rect. Now let's move to the config.py file. Within the configuration file, we're going to make sure that we are importing the components, and further below, we're going to create an instance of the class ground. The final thing that we need to do in order to draw the ground on our screen is to go to the main.py file, and in there, we're going to go within to the main loop, and we're going to call the draw function on the ground. If we now go ahead and run the project at this stage, you will see that we get a nice window, and within this window we have the ground. Now that we have successfully added the ground to the project, the next thing that we're going to work on is adding the pipes that move towards the player. These pipes are going to be spawning an equal distance apart every time, but the hole between the pipes is going to be different from one spawn to the next. To start off, we're going to import random into the components file. After that, we're going to go below the ground class, and we're going to create the new class called pipes. The width of the pipes is going to be 15 pixels, and the opening is going to be 100 pixels wide every time. Then we're going to define an init method, which takes the additional parameter window width. Whenever we instantiate a new pipe object, we want it to be displayed just off of the screen, which is why we're going to set self.x equal to the window width. The height of the bottom pipe is going to be a random integer somewhere between 10 and 300. The height of the top pipe, on the other hand, is going to be equal to the ground level minus the height of the bottom pipe minus the height of the opening. Next, we define the rectangles of the bottom pipe and the top pipe, and both are going to be Pygame rectangles with x and y coordinates and width and height all equal to 0. Then we're going to create two flags. The first flag is going to be called passed, and it is going to be set to true whenever the bird has passed through the pipe pair. And the second flag is going to be the off-screen flag, and it is going to be set to true whenever the pair of pipes has moved off of the screen. But by default, when the player gets initialized, both of these flags will be false. The next function we create is the draw function, and it is going to be responsible for drawing the pipes onto our screen. Starting with the bottom pipe, we're first going to create a Pygame rectangle. The x-coordinate is going to be self.x, the y-coordinate is going to be the difference between the ground level and the height of the bottom pipe. the width is going to be equal to self.width, and the height is going to be equal to self.bottom_height. Now that we have a rectangle, we need to draw it onto our screen, and we're going to do that using the pygame.draw.rect function, which takes 3 arguments. The first is where we want to draw the rectangle, which is within our window. That's the parameter we're also passing into the draw function. The next parameter is the color, and over here we're going to make it 255, 255, and 255, which is white. And finally, we have to pass in the rectangle we actually want to draw, and that's the one we just created, which is self.bottom_rect. Now that we've taken care of the bottom pipe, let's take care of the top pipe. Building the top pipe is going to be very similar to building the bottom pipe, so let's go ahead and copy and paste the code we just created for the bottom pipe. So first, let's go ahead and change the name to self.top_rect. For the pygame_rect, the x-coordinate is going to remain the same, but the y-coordinate is going to be set to 0. Then we're going to change the height to self.top_height. And finally, in the draw function, we need to reference the top rectangle. Since we want the pipes to move towards the left of the screen, we need to reduce their x-coordinate. The function responsible for this is going to be the update function, and it is going to have no other argument except for the instance itself. Within the function, we are going to decrease self.x by 1 every time the update function is called. In addition, let's add an if statement, which is going to check if self.x plus pipes.width is smaller than or equal to 50. And if this statement returns true, we're going to set the passed flag to true. The purpose of this flag is to mark the pipe pairs which the bird has passed. Now, at the moment, we've not yet created any bird or any player, but we will later on create one, and it is going to have the x-coordinate 50. So if a pair of pipes has a lower x value than 50, that means the pipes are to the left of the bird, which means they have been passed. The next if statement that I'm going to add is going to check if the x-coordinate of the pipe pair is smaller than or equal to the negative width of the pipes. And if that's true, we're going to set the self.offScreen flag to true. In essence, this flag is going to help us identify all the pipe pairs which have moved off of the screen and can be deleted. Now let's briefly move on to the config.py file, and all we're going to do here is we're going to set the pipes variable equal to an empty list. Within this list, we're simply going to store all the pipe pairs that get created. Now that we've created the pipes class, and we also have created a location within which we're going to be storing the pipe pairs, it is time to instantiate the pipe objects, and we're going to do that in the main.py file. And the first thing we're going to do there is we're going to import components, which is where we just created the pipes class. Then we can go on to create a function called generatePipes, and this function is simply going to append to the pipes list in the config module instances of the class pipe that we created earlier. Within the main function, we add a variable called pipesSpawnTime, and we set it equal to 10. Now within the main loop, we check if this variable is smaller than or equal to 0. If that is the case, we're going to call the generatePipes function and reset the pipe spawn time to 200. Outside of this if block, we're going to make sure that on every while loop iteration, we decrease the pipe spawn time by 1. Finally, we're going to add a for loop which loops through all the pipes in the config.pipes list. In this loop, we're going to call the draw function on the pipe, and remember that we have to add as an argument where we want to draw it, which is in the window, and we're also going to call the update function on the pipe, making it move to the left. And finally, remember that flag we set earlier, which checks whether a pair of pipes is off of the screen. Here we're going to reference that attribute, and if a pair of pipes is off of the screen, then we simply remove the pipes from the list. To see that we have successfully added the pipes, all we need to do is run this, and as you can see, we have the pipes moving to the left-hand side of the screen, which is exactly what we wanted. The next step in this project is going to involve creating some player, and we're going to keep it simple, and in our case the player is simply going to be a square. We're going to add all the code relating to the player.py file, so let's navigate to it. Within this file, we're going to import random, we're also going to import Pygame, and we're going to create a class called player. At the moment, the player class is going to have an init method, and this init method is going to have x and y coordinates that are going to be 50 and 200 respectively. We're also going to create self.rect, which is going to be a Pygame rectangle. The x and y coordinates of this rectangle are going to be equal to self.x and self.y, and the width and height are going to be equal to 20. The last attribute that we're going to add to the init method is going to be self.color, and it is going to be the color of the square that we draw on the screen. And this color is going to be an RGB value, which stands for red, green, and blue. Each component of the RGB color is going to be a random integer between 100 and 255. The lower boundary for each of these RGB values is going to be 100, simply for the reason that the background is black and we don't want the random color to be too dark. Next, under the heading Game-Related Functions, we're going to add one class method, which is going to be the draw function, and it takes as an argument the instance itself and the window. And in here we write pygame.draw.rect, and we pass in the arguments window, the self.color, and the self.rectangle, which we want to draw. Later, when we start introducing the AI to the game, we're going to realize that this player is part of a population of players. We're going to learn more about the algorithm later on in this video, but for now, let's just navigate to the population.py file. And within this file, we're going to import the config file, and we're going to import the player. Then we're going to create a class, and it's going to be called population. Within this population class, we have one init method, and we're going to write self.player is equal to player.player. So as you can see here in the init method, we are simply creating one instance of the class player. Besides the init method, we're also going to add the update live players function to this class. And this update function is going to run the draw function on the player. The remaining changes that we need to make in order to see the player on our window are going to be within the main.py file. Here we're going to import population, then we're going to create the variable name population, and it is going to store an instance of the class population. And since the constructor, so the init method of the population class, creates an instance of the player class, we are simply creating one player over here. The last thing we need to do is we need to draw the player on our screen, so further below in the while loop, we are going to call the update live players method on the population object. At this stage, you should see a small square appear on the left-hand side of our window, and that is going to be our player. Since we gave our player a random color, the color that you see here might be different to the one that you see on your screen. The next three things that we're going to add are the player movement, the collisions with the ground and the pipes, as well as the gravity pulling the player down. Let us navigate to the player.py file, and within that file we're going to import config. Then we're going to add a few more attributes to the init method. The first one is going to determine the y velocity of the bird. We're simply going to call it self.vel, which is short for velocity. Then we're going to add self.flap, and we're going to set it to false by default. This flag is going to be set to true whenever the player is performing one of those jumps that moves the player up the screen. And we're also going to add self.alive, which is equal to true, and this flag will be set to false whenever the player collides with the ground or a pipe. To distinguish between the attributes that have an influence on the state of our bird and the ones that relate to the AI, I'm going to write the comment bird at the top of these 6 attributes, and below I'm going to add the comment AI. And under the AI comment, I'm going to add one more attribute, which is going to be self.decision, and at the moment it is going to be equal to none. This attribute will be responsible for deciding whether or not the bird should flap, or in other words, jump, or not. Moving on, we're going to create the class methods that are necessary to detect collisions with the ground, the sky, and the pipes. To detect if a player has collided with the ground, we're going to add the ground collision function. Besides the instance itself, it also takes the ground as a parameter. And all that it does is return the value of the collideRect function between the rectangle of the player and the one of the ground. This way, the function will always return true whenever the rectangle of the player and the rectangle of the ground collide with one another. To make sure that the player does not fly into the sky endlessly, we need to add a sky collision function. This function is going to return true whenever the y value of the player rectangle is smaller than 30. The final collision that we need to handle is the one between the bird and the pipes. So let's define the function pipeCollision, and it does not take any additional arguments. This function is going to loop through all the pipes in the config.pipes list, and will return true if it detects a collision with either the bottom pipe or the top pipe. To check for a collision with the top pipe, we can write pygame.rect.collideRect, and then we pass in as an argument the rectangle of the player and the rectangle of the top pipe. But there can also be a collision with the bottom pipe, so let's write OR, and then pygame.rect.collideRect, and then as arguments we provide again the rectangle of the player and the one of the bottom pipe. Let us now create the update function, which also takes the ground as a parameter. And here we're going to take care of the gravity that acts on the bird and pulls it back towards the ground. Using an if statement, we're going to check that there has not been a collision with the ground or a collision with the pipes. And below that, we're going to handle the gravity, so we're going to increase self.vel by 0.25 every time the update function is called. Then we're also going to increase the y position of the rectangle of the bird by the self.vel value. Increasing the y value of the bird means that it is moving down the screen, and we're going to limit that value. So we're going to say that if self.vel is greater than 5, then we're going to cap it to self.vel equals 5. And then we're going to add an else statement. This is going to be relevant whenever the bird has collided with the ground or with the pipes. And so here we're going to set self.alive to false, self.flap to false, and self.vel to 0. To this point, we've taken care of the collisions and the gravity. The next thing we're going to look at is the flap of the bird, so the jump. We're going to define the function bird_flap, and it only takes the instance as an argument. Whenever this function is executed, the first thing we check if the bird is not flapping at the moment, and it is not colliding with the sky. And if this condition returns true, we're going to set self.flap to true, and we're going to set self.velocity to -5. Below that, we're going to add an if statement that checks if the velocity is greater than or equal to 3. And if that's true, then we're going to reset the flap variable to false. The last thing that we're going to do is we're going to add a comment, AI related functions, and below that we're going to have all the functions that relate to the AI. And the first function is going to be the function called think, which only takes the instance itself as an argument. Within this function, we're going to set the variable called decision equal to a random value between 0 and 1. The decision variable is the one that determines whether or not the player executes this upwards motion, otherwise known as the flap. Lower values that are below a certain threshold will mean that the player will not execute the flapping motion. And higher values, on the other hand, will mean that the bird will tend to flap its wings and jump. So now that we've talked about this threshold value, we also need to include it over here. Therefore, we're simply going to write that if self.decision is greater than 0.73, we're going to call the bird_flap function. By the way, you might be wondering why I use 0.73 over here. This is simply the result of trial and error, because later on when we add the AI, this parameter works really well, but we'll get into that later. The final thing that remains to be done in this step is to navigate to the population.py file. And in this file, we're going to go to the update live players function. And within there, we're going to add an if statement. We're going to write that if self.player.alive, then we want to execute the think function on the player. Then below the draw function, we're also going to call the update function on the player. And as an argument, we pass in the ground from the config file. So now when we execute this, you can see on the left-hand side that we have this one player which jumps along the screen. And once he hits either the pipes or the ground, he is deleted. Now that we have added one player to the game that acts randomly, we want to do that with an entire population of players. We need a population of players because this is one of the requirements for our algorithm to work properly. So within the population.py file, let's add another parameter to the init method, which is going to be the size of the population. Then within the init method, we're going to change self.player to self.players and set it equal to an empty list. Self.size is going to be equal to the size of the population that we enter as a parameter. Then we're going to add a for loop that adds the player objects to the player list above. So for I in the range of 0 to the size of the population, we want to append the player objects to the players list. Next, in the update live players function, we need to account for the fact that we have more than one player now. So let's create a for loop for p in self.players and then indent the if statement and replace self.player by p. Next, let's create the function called extinct, and this function is simply going to return true whenever all the players have been deleted. So here we can set extinct to true, and then we can loop through all the players and check if one of them is alive, and if there is a player who has the attribute alive set to true, we're going to set extinct to false. And at the end of this, we simply return extinct. Moving to the main.py file, we can add the size parameter to the population. We're simply going to make a population of 100 players, so let's enter 100 to the brackets. Further below in the main loop, we're now going to write, if not population extinct, we want to run the update live players function on the entire population. Else, we simply want to pass. So up to this point, we have now set up everything that we need to add the algorithm on top. Let's go ahead and run this once to see what the result is. As you can see now, I have a bunch of players that act completely randomly, and you can see that the players tend towards the top of the screen, and that is quite simply because I set the threshold to 0.73. If I had set it to 0.5, there would be an equal chance for them to go up or down, but at the moment they tend towards the top simply because the threshold value has been set quite high. Now we're going to add the AI in 2 steps. First off, we're going to create the neural network that controls the bird, and after that, we're going to add the natural selection process. So let's start with the first step and add the neural network which controls the bird. Before we go ahead and write the code for this, let me briefly explain what we're trying to do in this first step. Over on this image, you can see the input parameters that we are able to work with. The inputs I0 and I2 tell the player how far away he is in a vertical direction from the top pipe and the bottom pipe respectively. And the input I1 tells the player how far away he is from the pipes in a horizontal direction. Using these 3 input values, we want to generate one output value that tells the player to either flap, so jump, or not to flap, or not to jump. To generate this output value from the input values, we're going to be using a neural network, and we're going to be using the simplest possible neural network, which is called a perceptron. And here you can see the perceptron that we're going to build. You can clearly see that there are 4 inputs and 1 output. The inputs I0, I1, and I2, which we can also see on the image under the inputs, are called the bird's vision because they describe how the bird is positioned relative to the pipes. In addition to the bird's vision, so the inputs I0, I1, and I2, there is going to be one final input, I3, which is going to be the bias node, and its value is always going to be equal to 1. The input nodes that you can see on the diagram are going to be connected to one output node that generates the output value. And the connection between the input nodes and the output node is going to have some weight attributed to it. In our case, there's going to be 4 weights, 1 for every connection between an input node and the output. As you can see here, these are labeled W0 through to W3. And I might just add that the value of each of these individual weights is going to be somewhere between -1 and +1. The question that remains open is how can the output node generate one output from all the individual inputs and all the associated weights? And the answer to that question is given by the function that you can see down here, which is called the activation function. What happens is that we take the weighted sum of the inputs, as you can see here on the right-hand side of the equation, and we pass them into a function called the activation function. The activation function that I've labeled A takes the inputs and gives us an output between the values of 0 and 1. And now that we have this one output value, which is between the values of 0 and 1, the question becomes, how do we decide whether the player should flap its wings, or in other words, jump, or not? We do that using a threshold value, so whenever the value of the output exceeds the threshold, a jump or a flap is executed. But there is an additional condition, which is a jump cannot be executed when the player is currently in the middle of a jump. So in the example, you'll see that the jump is only executed whenever the flap variable is set to false and the output has a value beyond the threshold, which in this example is 0.8. Up until this point, we've covered all the theory concerning the first part of adding the AI, which is the neural network. Later on, we're going to add the natural selection process, but be patient, we'll get to that later. To build this neural network, let's start off by building the connections that we saw earlier in the diagram. The connection nodes that we're talking about are also frequently referred to as genes, and they describe what input node is connected to what output node. So within the file called connection.py, we're going to create the class connection. This class is not going to have any other method besides an init method. So we're going to define init, and the arguments are going to be the instance itself, the origin node called the from node, the destination node called the to node, and the weight of the connection. Further below, we're going to set self.fromNode equal to fromNode, self.toNode equal to toNode, and self.weight equal to the weight on the connection. Now that we've created the connections, let's move on to create the nodes that we also had earlier in the picture of the perceptron. So within the nodes file, the first thing we can do is import the library math because we're going to be needing the exponential function, so let's go ahead and add math in. Next up, we're going to create the class nodes, and we're going to start off by defining an init method, which besides the instance itself, also takes the ID number as a argument. We're going to set self.id equal to the ID number which we pass in as an argument. And the ID number of the node is quite simply a number between 0 and 3, which helps us identify which node we're talking about. So think back to the diagram from earlier, where the nodes 0, 1, and 2 characterize the bird's vision, and the node 3 characterize the bias node. Then we're going to set self.layer equal to 0, and this attribute simply describes what layer of the perceptron the node is on. The first layer with the index 0 has all the input nodes, and the second layer with the index 1 has that single output node. Moving on, we're going to set the value self.inputValue equal to 0 and self.outputValue equal to 0. And as the name suggests, these values simply describe what values go into the node and what goes out. And the last attribute that we're going to add is going to be self.connections, and we're going to set it equal to an empty list. This list is going to store all the outgoing connections that emerge from a node. Next, we're going to define the function called activate, and it only takes the instance itself as an argument. Within this function, we're going to define the function called sigmoid, which takes as an argument the value x, and it returns the output of the sigmoid function. So we are returning the value of 1 divided by 1 plus the exponential function to the power of minus x. Earlier we talked about the activation function, which takes the weighted inputs, puts them into the activation function, and returns an output value within our output node. To translate that into Python code, we're going to add an if statement, which is going to check if self.layer is equal to 1. In other words, if the layer which the node is on the output layer. And if that's true, we're going to set the output value equal to the result of the activation function. In other words, we're setting the output value equal to the result that emerges when we pass the weighted inputs into the activation function. and the weighted inputs are stored in the input value variable of the output node. The last thing that we need to figure out is how we can fill the input value variable of the output node with the weighted inputs. Because after all, that is exactly the value which we need to pass into the activation function to receive the output. To obtain this value, I'm going to create a for loop that I'm going to write down first and explain after. So let's go ahead and write for I in the range of 0 to the length of the connections list. And below that, we're going to access the input value of the destination node associated with the current connection that we're looking at. Then we're going to write the addition assignment. And last, we're going to write the product of the current connection's weight and the current node's output value. To briefly explain this for loop loops through all the connections in the connections list. And for each connection in the list, the loop adds the product of the connection's weight and the node's output value to the input value variable of the destination node associated with the connection. And remember, in our case, we only have one destination node because all the input nodes are connected to the same output node. Now that we've created the nodes and the connections, we have all the necessary components to create the neural net that makes up the brain of the player. That is exactly why we're going to go to the file brain.py, and in there we're going to start by importing the nodes, importing the connections, and besides that, we're also going to import the module random. Then we're going to continue by creating the class called brain. Within the brain, we're going to first define an init method, which takes two arguments. The first one is the instance itself, and the second one is the number of inputs. Below that, we're going to create an empty list called connections, and another empty list called nodes. These two lists are going to store the connections and nodes respectively that are required to build the player's brain. Then we're going to set self.inputs equal to the inputs that we pass in as an argument. And this is quite simply going to be the number of things that the player sees. And if you think back to the image from earlier where we had the bird and we talked about the inputs, we learned that there are 3. After that comes another empty list called nets. And this list is going to store the nodes that appear in the neural net, ordered by the layer that the nodes appear in. So at the beginning of this list, we'll have all the nodes that appear in the input layer, and at the end of this list, we're going to have the one node that comes in the output layer. And finally, we're going to set self.layers equal to 2. Still within the constructor, we're going to add a for loop that goes from the value 0 to self.inputs. And this for loop is going to append a node with the ID number I to the nodes list. And since this for loop is creating the input nodes, we're going to set the layer of the node that's being created to 0. Because remember, the layer 0 is defined as our input layer. We shouldn't forget that besides the inputs defined as the player's vision, we also have the bias node on the input layer that we still need to create. So to the nodes list, we're going to append a new node with the ID number 3. And of course below that, we're going to state that the third node in the nodes list, which is the node with the ID 3, is going to be in the layer 0. So now that we've created all the nodes on the input layer, the final node that remains to be created is the one on the output layer. Therefore, we're going to create a new node with the ID 4 and append it to the nodes list. And since this is the node on our output layer, we want to make sure that the layer is set to 1. The final thing that we need to create in the init method are the connections between the input nodes and the output node. So we're going to create a for loop in the range of 0 to 4 that appends a new connection to the connections list. We can do that by writing self connections append, and then in the parentheses we need to create a new instance of the connections class. And remember, when we create an instance of the class connection, we also need to make sure that we pass in the origin node, which is going to be node I, the destination node, which is going to be the node 4, and the weight on the connection, which is going to be a random number between the values -1 and 1. That is going to conclude our constructor function. Below the init function, we're going to define the next function called connect nodes. This function will be responsible for creating the relationship between a node and its outgoing connection. First, we're going to create a for loop with the variable I that ranges within the values of 0 and the length of the nodes list. And below that, we're going to reference the connections list within every node and set it equal to an empty list. Later on, when we add the natural selection process, this is going to make sure that our nodes don't have any connections from prior generations stored within them. And then we're going to create another for loop for the variable I, which ranges from the value 0 to the length of the connections list. And here we're going to loop through the origin nodes of each individual connection and then save it, and with it I mean the connection, to the connections list within the node object. And we can do that by writing self connections I from node, and then we access the connections list of the from node and append to it the connection with index I of the connections list. Then we're going to define the generate net function, and it is going to first execute the connect nodes function we just created above. Then it is going to set the net list to an empty list, and this will make sure that we delete any old nets that come from prior generations. This will become relevant when we add the natural selection process later on. Now we can add a nested for loop, so for j in the range of 0 to the number of layers, and for I in the range of 0 to the length of the nodes list. Within this, we're going to check if the node at the index I in the nodes list has the layer equal to j. And if that returns true, we're going to append to the net the node at the index I. This nested for loop is going to fill the net list with our nodes. And within the nets list, all the nodes are going to be ordered by their layer. So first, all the input nodes are going to be listed, and later the one output node. The final function that we're going to create within the brain class is going to be called feed forward. And besides the instance itself, it is also going to take the vision as a parameter. And this feed forward function is going to take care of a few things. The first thing it's going to do is that for each input node, it will set the value that it outputs. Accordingly, we can create a for loop that ranges through all the individual inputs, and then it will set the output value of the node with index I equal to the vision with the index I. Now remember, the vision of the player were quite simply the values that determine where the player is in relation to the pipes. Now that we have set all the output values of the player's vision, we also need to make sure that we set the output value of the bias node. So we're going to set the output value of the node at the index 3 equal to 1. The second thing that this feed forward function will do is that it will run the function called activate, which we created in the nodes class, on each individual node in the net list. We can create a for loop for the variable I that ranges from the value 0 to the length of the nets list. And below that, we can go ahead and activate the node, which is saved at the index I of the net list, and run the activate function on it. Remember that the activate function that we created earlier in the node class takes care of two things. The first thing that it does is that it takes the output value generated by an input node, multiplies that value with a connection weight, and then adds that value to the input value of the output node. And remember, it does that for all the individual input nodes, which generates the weighted inputs that we put into the activation function. And the second thing that it does is it takes the input value of the output node and runs that through the activation function, which is the sigmoid function. And once that's done, we receive the output value of the output node, which is going to be the value that determines whether the player flaps his wings and moves up the screen, or whether he doesn't do that and lets himself get pulled down to the bottom of the screen by gravity. So let's go ahead and create the variable called output value and set that equal to the output value of the output node. At the very end of this feed forward function, we want two last things to happen. First, we're going to reset the input values of all our nodes by creating a for loop with the variable I that ranges from the value 0 to the length of the nodes list and sets the input value of the node at the index I in the nodes list to 0. And at the very end, we're going to return the output value. So finally, after all this hard work, we've created the neural network, which is the brain of the player that we now need to add to the player. We're going to navigate to the player.py file, and in there, the first thing we're going to do is we're going to import the brain that we just built. Then we're going to add a couple more attributes to the constructor. So we're going to start off with self.vision, and we're going to set it equal to a list with the values 0.5, 1, and 0.5. These values describe the position of the player relative to the pipes, but don't worry about these values too much because later on we're going to create a function that updates these. Then we're going to set self.inputs equal to 3, and afterwards we're going to create the brain of the player by setting self.brain equal to an instance of the brain class. And as an argument, we're going to pass in self.inputs. Once we've created the brain object, we're going to run the function generateNet on it. Further below, I'm going to define the function closestPipe, and this is going to be a static method because it does not take the instance as an argument. And all this function is meant to do is return the pair of pipes that are closest to the player. So we're going to create a for loop that loops through all the pipes in the pipes list. And if we come across a pair of pipes where the past attribute is not set to true, then we're simply going to return these pair of pipes. As a result, this function will always return the pair of pipes that are closest to the player. The last function that I still need to define is the function called look, and it only takes the instance itself as an argument. This function is going to calculate the player's vision. This encompasses the vertical distance of the player to the top pipe and to the bottom pipe, as well as the horizontal distance of the player to the closest pipes. The distance between the player and the pipes can only be calculated if there are pipes on the screen, which is why we're going to start off by writing if config.pipes. Now let's start by calculating the distance between the player and the bottom part of the top pipe. So let's write self_vision0, and it is going to be calculated as the maximum value between either 0 or the difference between the y-coordinate of the player rectangle, which translates to self-rect center and then 1, and the y-coordinate of the bottommost point of the top pipe from the closest pair of pipes, which we can determine by calling the closest pipe function and then referencing the bottom of the top rectangle. And to receive a value between 0 and 1, we're going to divide this by 500. To make all of this more visual, we're also going to draw the line between the bird and the bottom point of the top pipe. And we can do that by calling PyGameDrawLine. And then as arguments, we first have to pass in where we want to draw this, which is the window, then also the color, and finally we also have to specify the origin and destination points for the line. The line is going to begin in the middle of the player, so we need to specify the x and y coordinates for that, which is going to be self-rect center. And the x and y coordinates of the destination point are going to be given by self-rect center 0 and config pipes 0, top rect, bottom, respectively. Now we have two things. We have calculated the vertical distance between the player and the bottom part of the top pipe, and we've also drawn a line that represents this. We need to do pretty much the exact same thing for the horizontal distance between the player and the closest pair of pipes, as well as the vertical distance between the player and the topmost part of the bottom pipe. And since the calculation of the distance and the drawing of the line works analogously to what we just learned, I'm simply going to paste in the code for that. So from what I've pasted in, you can see here the calculation of the horizontal distance between the player and the closest pair of pipes. And the line that visualizes this is created by this line of code over here. And similarly, the calculation of the distance between the player and the topmost part of the bottom pipe is given by this line over here, and the corresponding line is drawn by the line of code below that. Moving on to the think function, we can now replace the random value with a value that comes from our neural net. So we can delete the random uniform value between 0 and 1 over here, and add self brain feed forward, and then in brackets we pass in the vision parameters that we are calculating above. The very last thing that we need to do in order to complete this first part of adding the AI is to go to the population.py file. And then further below, we need to make sure that we call the look function on the player. So now when I go ahead and run this, you'll be able to see all the individual players jumping around. The difference between what we have now and what we had in the previous step is that now the jumps are determined by a neural network and not a random value anymore. And when you run this, you'll notice that as soon as all the players have hit the pipes or hit the ground, then there are no more players left and no new generations of players are created. But we don't want to rely on luck to create a player which is able to play by himself. That is why we're going to move to the second part of adding the AI, which is going to be adding the natural selection process. Before we jump into the code, I want to briefly explain how the natural selection process is going to work. We're going to start everything off with an initial generation of players that plays the game. All these players that are currently playing the game in this very first generation have the brain that we created earlier. And by chance, some of these individual players are going to get further than others. But soon enough, all the players from the initial generation are going to be dead because they either fell to the ground or because they bumped into a pipe. And once all the players are dead, the natural selection process starts with the very first step, which is called the speciation. And in this step, all the players that have played the game are going to be split into individual species depending on how similar the weights of their connections are. So remember that the neural network of each individual player has 4 connections between the input nodes and the output node, and each of these connections has 1 weight. To compare how similar these weights are between 2 different players, we can calculate the absolute difference between the corresponding weights of the brains of the 2 players and then sum it up. And that value is going to be called the total weight difference. And you can also see here from the formula in the middle how it is calculated. The smaller this number turns out to be, the higher the similarity between the 2 brains. And if this value turns out to be 0, that means the 2 brains that we are comparing are identical. To determine whether or not these 2 players that we are comparing are going to be within one species or not, we're going to have a threshold value for the total weight difference. If the total weight difference is below the threshold value, that means the player brains are similar and we're going to put both players into the same species. However, if the weight difference is larger than the threshold value, then we are going to create a new species. The end result of the speciation process is that we will have all our players grouped into different species. The players that belong to the same species are going to have very similar brains, but if we compare players from different species, their brains are going to be very different. And once the speciation process is over, the next step is going to be to calculate the fitness score of the individual players and of the species. The fitness score simply tells us how good a player or a species is. In other words, how fit they are. You might have already heard people referring to natural selection as survival of the fittest. And that's precisely what we're going to do. The fittest are going to survive. The fitness score of the players will simply depend on how long they stay alive. The longer a player stays alive, the higher his fitness score. And the fitness score of the species is simply going to be an average of all the fitness scores of the players that belong to a species. Once these fitness scores have been calculated, we're going to move to the next step in the natural selection process, and that is going to be to sort all the players within their species by their fitness, and then subsequently sort the species by their average fitness. Then comes the final step in the natural selection process, which is to generate the players for the next generation. The creation of the next generation begins by adding a clone of the very best player of each individual species. Then we're going to fill all the remaining open player slots by creating children for all the species that we have. To create a child, all we do is we select a random player from the species and then mutate his brain. We're going to look at the specifics of the mutation process later when we code it out. In any case, these children are also part of the next generation of players. And it can occur that at the end of this process, we still have vacant player slots. And we fill these by simply creating more children of the very best species until our limit is reached. And this concludes the natural selection process. At the very end of this process, we have a fresh generation of players that can start to play the game again. And this process repeats on and on and on until the players get so good that they play the game continuously without dying anymore. Now that we know what the natural selection process is going to look like, let's jump back into the project and add this. Within the main.py file, I'm going to scroll down to the main loop, and specifically I want to go to the place where we have the if-else statement, which is going to decide whether we update the players that are currently alive or whether we run the natural selection process. Earlier, we wrote pass under this else statement over here, but we want to replace that with two things. The first thing that we want to happen when the population goes extinct is that we want to delete all the pipes within the pipes list. That's going to make sure that when we run the new generation of players, there's not going to be any pipes from previous games from prior generations. The second thing we want to include is we want to call the natural selection function on the population. And we're going to create that function within the population file in just a moment. So let's now move to the population.py file where we want to begin by importing math, importing species, and importing operator. Subsequently, in the init function of the population class, we want to add two more attributes. The first one is the generation, which is going to be equal to 1, and species, which is going to be equal to an empty list. Further below, under the update live players function, we're going to define the function called natural selection, which only takes the instance itself as an argument. Within the natural selection process, we're going to include all the individual steps that I went through individually in the explanation earlier. First off, we're going to add a print statement which prints speciate so that we know that the speciation process has started. Then we're going to call the speciate function by writing self.speciate. Once the speciation process is done, we need to calculate the fitness of the players and of the species. So again, we can write a print statement, calculate fitness, and then call the calculate fitness function. After calculating the fitness of the players and the fitness of the species, we want to proceed by sorting the players by their fitness and sorting the species by their fitness. So let's go ahead and write print sort by fitness. And below that, we're going to call the function sort species by fitness. And in the final step of the natural selection process, we want to create the children for the next generation. So let's go ahead and write a print statement, children for next gen, and below that, we're going to write self.nextgen. Now we have created 4 function calls to the individual steps of the natural selection process. We've created a call to the speciate function, the calculate fitness function, the sort species by fitness function, and the nextgen function. In the next step, we need to create these functions. So let's go ahead and define the function speciate. Within the function definition, we're going to create a for loop that loops through all the species s in self-species. And we're going to set s.players equal to an empty list. So all this for loop does is that it deletes all the players that are associated to a specific species. We need to do that because when we run this game for multiple generations, we're going to be creating species every time. But we don't want the species from a prior generation to interfere with the species from the current generation. Moving on, we're going to create a for loop, which is going to go through each of the players that exists. And for each player, we need to decide whether we want to take him and allocate him to an existing species, or whether we take him as the basis for a new species. So let's go ahead and create a for loop that loops through all the players p in self.players. Below that, we're going to add a flag called add to species, and we're going to set it to false. Then we're going to create another for loop that loops through the species s in self.species. This next if statement is going to determine whether the player is added to an existing species or not. So let's go ahead and write if, and then s.similarity, and pass in the player's brain. We're going to create this function later on in the video, but what you should know is that the similarity function determines whether the player's brain is similar enough to be added to the specific species that is being iterated through in the for loop. And if the condition is true, we want to call on s the add to species function and as an argument pass in the player. That way the player is going to be added to the species. And if that's the case, we want to set the add to species flag to true and then break out of the for loop. Below that, we're going to add another if statement which checks the state of the add to species flag. Specifically, if the add to species flag has not been set to true, we know that we need to create a new species on the basis of the player. We can do that by writing if not add to species, and then in that if statement, we can write self.species.append, and as an argument, we pass in an instance of the species class, which we still need to create. That's the speciate function done. The next one we need to take care of is the calculate fitness function. So let's go ahead and define the function calculate fitness, and below that, we're going to create two for loops. The first for loop is going to loop through all the players P in self players, and then call the calculate fitness function on each individual player. Next up, in the second for loop, we're going to iterate through all the species S in the self.species list and call the calculate average fitness function on the species. Next up, we need to sort both the players and the species by fitness. To do that, we define the function sort species by fitness. Then we're going to add a for loop that loops through all the species in the self.species list. And on each of the species S, we're going to call the sort players by fitness function. Subsequently, we're going to sort the species by fitness. And here we're going to use the attribute getter function from the operator module. This allows us to sort instances of a class by a specific attribute. So here we can write self.species.sort, and within brackets, we're going to first add a key, and we're going to set that equal to operator.attributeGetter. And the attribute we want to sort by is the benchmark fitness. And since we want to sort from highest to lowest, we need to set reverse to true. The final function we need to take care of is called nextGen. This function will take care of creating the children for the next generation in the natural selection process. So let's go ahead and define the nextGen function, and below that we're going to set children equal to an empty list. Basically, this is to make sure that we don't have any children from prior generations interfering with the children we're generating in the current generation. To begin, we're going to be cloning the champion of each species into the new generation. So we can write for s in self species and then append to the children's list a clone of the champion of the species s. Then we need to determine the number of children from each species that goes into the next generation. Therefore, we're going to create the variable children per species. And we'll set that equal to math.floor. And in parentheses, we're first going to calculate the difference between self.size and the length of the species list. And the result is going to be divided by the length of the species list. Then we can create a for loop that loops through all the species S in the self.species list, and another for loop within that for the variable I that ranges from 0 to children per species. And within that second for loop, we're going to write children.append s.offspring. After that, we can go ahead and check if there are any more free slots in our next generation. We can write while the length of the children's list is smaller than self.size, we want to go ahead and append to the children's list offspring from the best species. After we have created all the children that should be in the next generation, we can set self.players equal to an empty list, which makes sure that the players list is completely empty. And then we can create a for loop for child and children that appends to the children's list all the children. And at the very end, we can still increment the generation counter. That's all we need to do in the population.py file, so let's move on to the species.py file. Here we're going to begin by importing operator and importing random. Below that, we can start off by creating the class species, and we're going to start with an init function. So let's define init, and we're going to take as arguments the instance itself, as well as the argument player. Now let's create the necessary attributes. First off, we need a list that stores all the players that belong to a species. So we're going to write self.players equals an empty list. We're also going to create average fitness and set that to 0. This variable is going to store the average fitness across all the individual players in the species. Next up, we're going to create the value threshold and set it to 1.2. We're going to use this threshold value later on when we decide what players are going to be added to the species and what players are not. After that, we're also going to append to the players list the player that gets passed in as an argument. Then comes the benchmark fitness, which we're going to set equal to the fitness of the player that we pass in as an argument. And the benchmark brain is going to be set equal to player.brain.clone. And finally, we're going to store the player with the highest fitness in every species as the champion. So we're going to write self.champion is equal to player.clone. Then we can define the function similarity, which takes as an argument the instance itself and the brain. And this function will be responsible for comparing the brain that gets passed in as an argument and the benchmark brain of the species. So below the function definition, we're going to write similarity is equal to self.weight difference, and then as an argument, we first pass in the benchmark brain, and second, the brain, which we add as an argument. And we're going to return a Boolean value that is simply going to check if self.threshold is greater than the value of similarity. After that, we're going to add a static method to this class. That simply means that we're going to define a function which does not take the instance itself as an argument. Specifically, we're going to define the function weight difference, which takes as an argument the brain number 1 and the brain number 2. All this function is going to do is sum up the absolute differences between the connection weights of both brains. To do that, we first define the total weight difference and set it equal to 0. Then we create a first for loop for the variable I, which ranges between the values 0 and the length of the connections list of the first brain. And within that, we add a second for loop for the variable j in the range of 0 to the length of the connections list of the second brain. And then with an if statement, we check if the index I and j are equal. Because if that's true, then we're looking at equivalent connections in the two different brains. So then underneath that, we can write total weight difference and then add to that the absolute difference between brain 1 connections I weight and brain 2 connections j weight. And at the very end, we can return the total weight difference. The next function that we need is the function add to species, which besides the instance itself, also takes the player as an argument. Below that, we can write self players append and then in brackets player. So this function will allow us to add players to a specific species. Moving on, we're going to define the function sort players by fitness. As the name of this function already suggests, this function is going to be responsible for sorting all the players in the players list by their fitness. That can be accomplished by writing self players sort, and then within parentheses, we set the key equal to the operator attribute getter fitness, and then reverse equal to true. And once that's done, we're going to check with an if statement if self player 0 fitness is greater than the benchmark fitness which we currently have. And if that's true, we want to set self benchmark fitness equal to self player 0 fitness, as well as self.champion equal to self player0.clone. Next, we need to add a function that calculates the average fitness across the players that are within one species. So let's define the function calculate average fitness, and below that, set total fitness equal to 0. After that, we're going to add a for loop that gathers all the fitness scores of all the players within the species. So we can write for P in self players, and below that, total fitness, and then add p.fitness. This small for loop is going to allow us to sum up all the fitness scores of the players within a species. Then, with an if statement, we're going to check if there are any players within the players list of the species. So we can write if self.players, and below that, we can calculate the average fitness by writing self.averageFitness is equal to the integer value of the total fitness divided by the length of the players list. And for the case that there are no players within the species, we have an else statement, and below that we can simply write self.averageFitness is equal to 0, which simply means that if there are no players for a species, we set the average fitness of the entire species to 0. And the very last function we need in the species class is a function that creates children for the next generation. So let's define the function offspring, and this function only takes as an argument the instance itself. Below that, we need to do two things. The first thing is we need to take a random player that is within this species and clone him. And besides that, we need to mutate his brain. So let's start off with the cloning. Let's create the variable baby, and we're going to set that equal to self players, and we're going to choose a random player. So let's write random.randint, and we're going to choose a random player between the values of 1 and the self.players list length minus 1. And at the very end, we're going to run the clone function on this player. You might be wondering why I'm not starting with the index 0 when choosing a random player from the players list. And that is because the player with the index 0 in the players list is our champion. It is the player with the highest fitness score. And earlier, when we were coding the population class, we already created a clone of the champion and added him to the children. That is why we exclude the player with the index 0 over here. The next thing that we need to do is to mutate the baby's brain. We do that by writing baby brain and then calling the mutate function. And subsequently, we simply return baby. Now that we're done with the species class, let us move to the player.py file and go into the player class for a moment. Here we're going to add a few more attributes. The first one is going to be lifespan, and we're going to set it equal to 0. The lifespan is simply going to be a measure of how long the player has stayed alive. Besides that, we're also going to create the attribute called fitness and set it equal to 0. Further below in the update function, we're going to increment the lifespan. That means we're going to write self.lifespan and then add 1 to it. So every time we call the update function on the player, we're going to increment the lifespan attribute by 1. And this happens once for every iteration of the main loop. And remember, the main loop is the one that we created earlier in the main.py file. So this attribute is going to give us some indication of how long the player has stayed alive for. And somewhere near the end of the player.py file, we're going to define the function calculateFitness. And all this is going to do is it's going to set self.fitness equal to self.lifespan. And the final thing that we need in the player class is some possibility to clone a player. We need this because it is part of the process of creating children for the next generations. So let's define the function clone, and below that, we're going to set clone equal to an instance of the player class. After that, we're going to set clone.fitness equal to self.fitness, and clone.brain equal to self-brain-clone. And then we are going to write clone, brain, and generate net. And at the very end, we simply return the clone. Let's now move on to the brain.py file, where we're going to make a couple of changes to the brain class. Whenever we create a clone, we don't need to create input nodes, output nodes, or connections, because they've been copied. To account for that, we're going to add another argument to the init method, which is clone, and we're going to set it to false by default. And further below, we're going to add an if statement, if not clone. And then we want to indent the for loop, which is responsible for creating the input nodes, the bias nodes, and the output node, as well as the for loop that creates the connections between the inputs and the output. That way, new inputs, outputs, and connections are only going to be created if we are not dealing with a cloned brain. Further below, we're going to define the function clone that only takes the instance itself as an argument. Below that, we're going to create the variable clone and set that equal to an instance of the brain class. The first argument we have to put in is self.inputs, and the second one is true because it's going to be a clone. To clone all of the nodes, we're going to append to the nodes list a clone of all the nodes. So let's create a for loop for n in self nodes, and below that we can write clone nodes append, and then in brackets n.clone. After that, we need to make sure that we also clone all of the connections, which we can again do with a for loop. So for c in self connections. And then we're going to append to the connections list of the clone the individual connections between the from nodes and the to nodes, which are the origin nodes and the destination nodes. After that, we want to set clone.layer equal to self.layer, and then we need to connect the nodes by running the connect nodes function on the clone. At the very end, we can simply return the clone. Further below, we can define the function getNode, which takes as an argument the instance itself and the ID. All this function will do is take in an ID and return the corresponding node. We can accomplish that with a for loop, so for a node n in self nodes, and if the node ID is equal to the ID that was passed in as an argument, we're going to return the node n. And at the very end of our brain class, we're going to define the function mutate, and this function only takes the instance itself as an argument. The mutation process will not always occur. It will occur with a probability of 80%. We can accomplish this by writing if random uniform within 0 and 1 is smaller than 0.8. And if that's true, we're going to have a for loop for I in the ranges of 0 to the length of the connections list, and we're going to call the mutate weight function on the individual connections in the connections list. The last changes that we need to make and the last functions that we need to add are going to be within the connection class and the node class. Let's start off with the connections class. Within the connection file, we're going to import random. And then further below, we're going to add the function called mutate weight. The mutate weight function is going to change the weights on the individual connections. There's going to be a 10% chance for a large change and a 90% chance of a very small change. For the very large change, we can simply state that if random uniform between 0 and 1 is smaller than 0.1, then we want to take self.weight and set it equal to a random value between -1 and 1. The small change is going to be accounted for within this else statement, and here we're going to have self.weight and add to that a random value from the Gaussian distribution with a mean of 0 and a variance of 1 divided by 10. And since the weights always need to have the values between -1 and 1, we're going to have an if statement that states that if self.weight is greater than 1, we want to set self.weight equal to 1. And if self.weight is smaller than -1, we set self.weight equal to -1. At the end of the connections class, we want to have a possibility to clone the connection. So let's define the function clone, and it takes as an argument the instance itself, a origin node called from node, and a destination node called to node. And below that, we can set the variable clone equal to an instance of the connection class with the arguments from node, to node, and self.weight. And after that, we can simply return the clone. Finally, we're going to move on to the node.py file, where we're going to make a change to the node class. Here we need to add some sort of possibility to clone the node. So just like we did in the connections class, we're going to add a function called clone, and this will allow us to make a clone of the node. So below the function definition, we can set clone equal to an instance of the node class, and as an argument, we're going to pass in the ID. Then we're going to set clone.id equal to self.id. After that, clone.layer equal to self.layer. And finally, we can return the cloned node. And this actually concludes all the changes that we needed to make in order to add the natural selection process to our project. If I go ahead and run this now, you can see that we have the players playing the game. And the interesting thing is that in contrast to what we had earlier, where when all the players died, the game would end, we now have the natural selection process taking place. That means if all the players die, a new generation is created and we continue playing. And if I speed up this footage and let the game play for a couple of generations, the AI gradually learns through the process of natural selection, and soon enough there's going to be a player that is able to play the entire game and does not die anymore. To round off this project and make sure that everything is running smoothly, there are two final things that I want to add. First, I want to make sure that we delete any species that do not have any players. And second, I want to make the algorithm more efficient by deleting any species that don't improve after a certain number of generations. So let's start with the first point and delete any species that do not have any players associated with them. Because if we do not, there are some rare cases where this leads to an error. So within the population class, let's go to the natural selection and add a print statement which says kill extinct. And below we'll add a call to the kill extinct species function. So then further below, under the calculate fitness function, we can define the function kill extinct species, which only takes the instance itself as an argument. Here we're going to create a variable called species bin and set it equal to an empty list. Then we're going to add a for loop for the species s in self.species, and within this for loop we're going to check if the length of the players list for a species s is equal to 0. And if that's true, then we want to append to the species bin the species s. And at the very end we want to remove all the species from the species bin. So let's create another for loop for the species s in the species bin. We can simply write self species remove and then s. So this is the first adjustment done, and this will always make sure that there is no species that have no players. The next adjustment that I want to make is actually an optimization to the algorithm. I want to make sure that any species that does not improve for a certain number of generations is deleted. So back in the natural selection function, we're going to write a print statement that prints kill stale. And below that, we're going to create a call to the function called kill stale species. Then just below the kill extinct species function we just created, we're going to define the function kill stale species. And here we're going to create the player bin and set it equal to an empty list. And then we're going to create the species bin and also set that equal to an empty list. Then let's add a for loop for the species s in self.species. And here we're going to check if the staleness of the species is greater than or equal to 8. If that is the case, then we want to check that the species that we're deleting isn't the last one that exists. We can do that by checking if the length of the species list is longer than the length of the species bin plus 1. And if that's true, we can write species bin append s. And in addition, we can create a for loop that loops through all the players p in the players list and subsequently appends the player to the players bin. However, if it's not true, then in an else statement, we're going to set the staleness of the species to 0. And at the end, we want to create a for loop that loops through the players p in the players bin and removes the players from the players list. And we want to create a for loop that loops through all the species s in the species bin and then removes the species from the species list. The very last thing we need to do is we need to implement the staleness in the species class. So let's navigate to the species class and add an attribute self-staleness and set it equal to 0. Then below in the sort players by fitness function, we want to set self.staleness to 0 if one of the players of the species has attained a higher fitness than the benchmark. On the other hand, if there has not been an improvement, we want to have an else statement and we want to increment the staleness by 1. And that was the very final change that we needed to make. Now when we run the game, everything works perfectly. So the players have the feed forward neural networks implemented and they are gradually learning how to play the game through the process of natural selection. So for one last time, let me speed up this footage and let me show you that the players gradually learn how to play this game. You can see that from one generation to the next, the players gradually improve through the process of natural selection. And the end result of this is that we find a player that does not hit the pipes anymore or the ground and is able to play the game perfectly. If you enjoyed this video and would like to see more similar videos in the future, then let me know by leaving a like under this video and subscribing to the channel.